Thanks, John, for, for the intro. I'm Davide, and today I'm going to talk about how we can use brain stimulation and whole brain model for unveiling the underlying different strategy that brain network have to send, integrate, and receive information. No disclosure. So, as a neuroscientist, from one side we have the anatomical connectivity, and from the other side we have the functional dynamics that originate from the scaffold. And a compelling way for studying this interaction is taking the brain with the structural connectivity, send like an external perturbation, and then studying the functional dynamics that originates as a function of this perturbation. So this is, for example, a way for doing that. A compelling way for studying this propagation pattern is recording the EEG and then stimulating the brain, in this case with TMS, but can be like any sort of brain stimulation technique, and study the propagation pattern that originates as a function of this perturbation. So there are very awesome papers out there that have shown how this measure of propagation can be very relevant for clinical purposes. For example, also Anna Catani mentioned how in the context of coma, we can use this TMS EEG measure in this case for seeing that, for distinguish between a healthy state and coma and or deep sleep. As you can see, in a healthy state, there is like a propagation pattern. So in this case, there is a vivid mental life in the participants. In this case, there is no consciousness because we perturb the brain and we record what is called like a sleep-like waves. So the brain responds right here, but then is not responsive anymore. Okay, so we use brain stimulation. So we have this sort of perturbation that we inject in the brain, and we evoke some sort of propagation pattern and this recurrent activity. And recurrence is like everywhere. It's like in science, like in life in general, in art. So the kind of question that we have, which was what is the genesis of this activity that we record as a function of the brain stimulation that we inject? And to answer this question, we use a computational model. And in this case, I don't have the time to go to like the derivation and the equation, but we use the Janssen and Ritz model, which is a physiological model. As you can see, he has like a pyramidal cell and interneuron, which are excitatory and inhibitory. The take-home message here, we inject the input in some region, and we study like the propagation pattern that originates as a function of this perturbation. So we took this model, right? So this slide is methodological. So keep the icon open because it's gonna be the method for all the stuff that I'm gonna present. So we took this model and we stuck this model in a 200 parcellation. So we divide the brain in several regions, and in every region we put like this model. And then the connectivity between the parcel was modeled with the DWI image, so diffusion. And we simulate the activity at the level of the parcel, and then we invert the model for simulating the EEG. And as you can see at the very beginning, there was not a good fit between the simulated EEG and the ground truth, so the empirical, here at the bottom right. So we use a computational, we cast the equation in a PyTorch environment, so we use deep learning and machine learning for updating the parameter of the model, and we come out after like the fitting with a good fit between the simulation and the empirical. And we use this framework for answering the question that regarding the origin of the network. And we, for example, have shown that if we run the simulation and we create some virtual lesion in silico, so we create some lesion in the structural connectivity, we were able to suppress the late responses, which was kind of similar to what, as I told you before, people have shown like in clinical. As you can see, here the cortex responds initially, but then there is a suppression of the responses, which is something that we are able to like reproduce in silico in this paper. But we move forward, and as you may know, right, like the activity, the spontaneous activity is well organized in the resting state network, and there are several like great contribution in literature that shown how this like network structure is kind of hierarchical in certain ways. So we have like high order network, which are default mode, frontoparietal, and they are characterized by functional integration. And they kind of rely on the bottom of this pyramid, which is low order network, which are on the other hand characterized by functional segregation. So the kind of question that we have, it was what are the differences in the propagation pattern between different networks? And we use collaboration with the University of Milan with this data set when there are 323 sessions coming from 36 implanted patients. So those are patients that have intracranial recordings and extracranial recordings, so high density EEG. We stimulate intracranially, so this is stands for single pulse electric stimulation, here, 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 and we record intracranially and extracranially. So we basically saw a kind of map when the stimulus was delivered, so what network we stimulate specifically, and then we divide the 323 sessions depending on what network we perturb. And then what we saw, this is just for show you like the average of the activity. We basically see that we kind of, regardless of the network that we perturb, we kind of were able to record similar like evoked potential compared to like what, for example, the group of Parvisi have shown. So we have these three clusters. So what are the differences in these three clusters depending on the network that we perturb? So what we found was basically that this is the take-off message. So for the late responses, so the response that come like after 100, 200 milliseconds after the pulse, we found that for the high order network, so default mode and frontoparietal, there was a stronger response compared to the low order network, which are visuospatial and somatomotor in this case. And we found this both for intracranial EEG and extracranial EEG. And this is kind of reiterate what people have found in literature with other modality, functional MRI. We show this like with brain stimulation data, electrophysiological data. So the next step was, okay, so this is kind of a summary. We show in the empirical data set that different networks have different responses, and specifically high order network have higher, stronger responses for the late component compared to low order network. So the next question was, what are those differences characterized by different strategy that network have to receive, integrate, and send information? So for answering the second question, we use a computational model in the same framework that I showed you before. So we fit like the model, we see our machine learning approach, and then we create some virtual legion to the structural connectome. And in this case, we create a virtual legion for isolating the network that we stimulate, and this is an example where when we isolate the low order network, so the network is only able to speak with itself, but not able to speak with the rest of the brain. And we kind of expect, for example, for low order network, we expect a preserved later ERP, so no changes compared to the ground truth. In a sense, the information kind of rely to itself. It doesn't need like information from the rest of the brain. On the other hand, if we create the same legion to like the high order network, so the actually top of this pyramid, we kind of expect a suppression of the response because those networks are characterized by functional integration and the kind of rely of the bottom of this pyramid. So this is those are the results. So in the dashed line, I cannot use the point. Okay. So the dashed line is the simulation run with the interstructural connectome, and the solid line is the disconnected connectome. And we did this for all the network. As you can see, like for the bottom of the pyramid, so for the low order network, there are some changes, but are not significant compared when we run the simulation with the interstructural connectome. So the legion doesn't really affect the propagation pattern, meaning that those networks like here or mainly rely to like information that comes from the network, from their own parcel. On the other hand, like if we look at the high-order network, so the actually top of this pyramid, we found a suppression of the responses, especially the late one, meaning that those responses right here rely on like some information that comes out from the network. So those are, we basically disentangle different strategy that the network have to like receive it, integrate, and send information depending if they are at the top or the bottom of this pyramid. And those are, just to reiterate, those are the differences in the area under the curve if we measure like intact versus disconnected structural connectome. So this is just a recap. So I show you how basically connectome is essential for shaping the responses and how both shape and both space and time are important for shaping the propagation pattern. And then I show you how basically like there are different responses depending of what network we perturb in the empirical data. And then I show you how basically we can kind of disentangle between the strategy that the network use for like kind of sending the information depending on using a computational model. So this is just for show you that everything that I presented is open source and replicable, and if you notice any like similarity between this log and other publish, is completely due by chance. And I want to say like thank you to like all our collaborator and of course like to the group. Yeah, thanks.
We have a little time for questions, so I do invite anyone who has something burning to step up to the mic. Yes, Kaio is inspired. What have you got for us, Kaio?
Hi, thank you. That was so cool. I was curious to know whether the depression in the response in the high-order networks, when you take out the connections, is related to the number of connections you actually take out. In other words, are the higher order networks more connected to the outside of the connectome, and could that perhaps explain a bit of that?
Yeah, this is a good question. So for the number of connectivity in general, like the visual network, for example, is the one that has more streamline by definition. But yeah, you are right. It's probably like due to the connectivity and how much they are kind of connected with the outside compared to the inside. That's a very good point. Yes.
Cool. Thank you so much.
Sure.
Amazing.
Thanks.
Thank you. Good point there, Kaio. Okay, so if no one else is jumping up in excitement to the microphone, then we'll give Davide another round of applause and move along to our next speaker.